Hello again. So for today's topic, we're going to be exploring and developing the use of biomes in procedural generation. We will develop simple offline procedural biomes in conjunction with the already present procedurally generated map. Now, as we are doing biomes, Minecraft becomes a very good candidate for generating biomes. It utilizes the generation of flora based on the varying geographical features including humidity, temperature, and height. In this case, we'll be focusing on height as a driving factor for our biomes, with a max altitude defining the area which is similar to a snow biome, a warm temperate area which defines the majority of the placement of plants, and a sea level which is the lowest area where plants can spawn in. Now to start off, we'll begin setting up the scene. Firstly, set up your lighting, then with the already made procedural maps generator, we drag the class actor into the scene along with the AI manager and our player. Before we regenerate, make sure that the enemy character blueprint is assigned to our AI manager. From there, we just regenerate the map and drag our player high enough to land onto our map. Now that we can begin working on the biome, we firstly need to develop our primitive spheres that will be our indicator for which altitude or temperature point it is generated at. For this actor, we make a C++ class inheriting the actor class, and in its constructor, we give it a scene component as a root and static mesh component for our mesh. Then assigning it a static sphere using the object finder. Then set up a function that takes a pointer to U material and assigns it to the mesh where we spawn the sphere. From this, whenever the biome is regenerated, the test spheres will be in colors that are corresponding to the separate biomes or altitudes that we are generating. Next we are going to set up the Biome Generator class. This will handle the population of the spawn items such as plants and the test spheres into the scene. Firstly, we define the variables. Now we've got two actor arrays that both take the spawn primitives and the terrain foliage we will make later. In this case will be the trees. This is then followed by numerous float variables that define our sea level, minimum scale, maximum scale, altitude, allowed slope angle, three bool variables that will be our switches, a variable which will store our reference to the procedurally generated map class, two subclass variables to the class actor references that we'll use for our generation, and a series of materials that will be used to color our test spheres. As of last time, these are a quick capture of functions that will be used for this class that we'll go over during this tutorial. Now, in its constructor, provide the variable defaults that are listed on the screen. We then follow this with including the shouldTick viewport only after the tick function so that the class can run in the editor. From there, we can begin working on the methods for this class. Firstly, make a clearMap function which takes the variable arrays and empties them before regeneration. Then we add the functionality which will enable the spawning of our test spheres. So next we create our spawnPlant function which firstly iterates over the instances of our primitive object and destroys them from the scene. After destroying the instances, we then iterate over both rows and columns using a for loop. In this loop, it runs an if statement to run the checkValidSlope function, which returns a bool. And once done, we store the vertex position from the vertices argument, and if enabled, we run the function spawnTestPrimitives. But there are two things that we must check over beforehand. Firstly, in the function checkValidSlopePosition, we run a series of statements similar to the AI manager, which checks for both corner and edge cases for each position we iterate. In these checks, we run a checkValidAngle function that takes the current node position and the positions of nodes forward and right relative to the current position. Now, basically in this function, we check whether the normalized direction is within the specified allowed angle, which either returns true or false. With that Boolean value, the spawnPlants function then uses it to spawn the objects. From here, We then create our spawn test primitive class, which spawns an instance of our primitive object class and assigns it a material. These three materials signify whether the object is above max altitude, within the warm region, and whether it is below sea level. After this, we then go back into our tick function, and if we're generating the map, we first clear the map of objects and then get the list of vertices from the procedurally generated map class. We then pass it into the spawn plants class alongside the width and the height of the procedurally generated maps class. Then lastly, we check the BRegenerate map to false when we're done. With that over, we then head into the editor and add in an instance of our C++ actor into the scene. We then set the desired variables to however you like. However, set the allowed angle to 0.5 and then assign an instance of the procedurally generated map into the corresponding variable. Additionally, you'd want to make 3 different simple materials colored dark blue, white, and green for the 3 corresponding areas of our scene. Then select the primitive object from the basic sphere dropdown. With the editor set to real time, press the regenerate maps boolean, which will then generate spheres on different points of the map. As you look around, you'll notice that there are gaps around the sloped areas. That's the function preventing the spheres from being spawned on slopes, enabling for the objects to spawn in green areas of our map. If needing to regenerate on a different map, regenerate the procedurally generated map first, and then again regenerate the biome's objects after, since it's an offline process. And from there, you got yourself the basic gist of how it generally works. But here we are missing some trees and a feel of the landscape that the scene really needs. Now we go ahead and make another class called Plant Terrain Actor. Now this class will be vastly similar to the primitive object, but with just a few differences. In the Plant Terrain Actor header file, the class is made as a blueprint spawnable component just above the Plant Terrain Actor class name, as this will be a blueprint component. Additionally, as the model I've imported contained its own material, the class also does not contain its own materials variable, and contains methods towards both setting position and scale. However, for this demonstration, only one will be used. Now, in its constructor, we do the same and create our own using component with a starting scale of 1.5. And like the primitive class, its own mesh component is attached to the using component as its root. Lastly, we write the setScale function, which ensures to check for a location component in the actor and sets the specified scale from the argument. Back into our Biome Generator, we create another class called DetermineBiomeSpawn, which is responsible for regenerating foliage and trees. However, for this example, it'll be only generating trees in the warm areas of the map. Now, as this is similar to the spawn test primitives function, we avoid spawning trees in sea level and above the max altitude. In here, you can decide to put underwater coral or even plants that only exist in higher altitudes. Then from here, we then call the spawn actor function to generate the plant class on generation and set the scale to the random scale decided between the minimum and maximum range. We then end this function with adding it into the array. Likewise to spawning primitives, this function is called in the spawn plants function, only being generated if the BGenerateFoliage boolean is true. However, as we are using imported models, the pivot location may be offset from the center. We can fix this from the import window, but I prefer to quickly modify it by making a blueprint through the Plant Terrain Actor class. With this, we select the mesh component, then add in the imported mesh under the static mesh header. Once completed, I then modify its offset in the viewport to be in the center. With this, you can also use the same approach to make other blueprints containing the same class but with different meshes. Lastly, in our Biome Generator instance, we assign the blueprint in the dropdown of the tree object variable. And with that, it completes the implementation. Thus, with checking the generate foliage boolean and unchecking the generate test sphere boolean, we can begin populating the trees once we regenerate the terrain. Following on with the test spheres, the map and trees can be regenerated to suit different map creations. And with that, our simple biome generator is completed. Now, as this continues from the previous project, it presents many opportunities of creating more interesting environments than a plain empty map. This can be also utilized with AI for it to navigate around the map that is generated. However, as the objects spawn above the points of the terrain, it limits the locations that it can move along. Much of the development was a learning experience, thus it was mostly kept localized in its own class, to only refer to details from the work done from the labs and from assessment 2, completed beforehand. And as my teammate is developing a spellcasting system utilizing a generator to affect its spell characteristics, these overall game features can improve the overall experience. However, we aim to build further upon this to add in improvements, but also to expand on what is already currently generated to make more dynamic environments, as well as to expand on the previous assignments and as well as the core features that were defined in the lab assignments too. Thus, there you have it, a simple offline biome generator. I hope you find it useful and insightful into its potential uses. And then again, thanks for listening and hope you have a good one.